Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics. In this last lecture, in this series, I will be discussing the following points. So, the contents are dispersion relation, inelastic neutron scattering, difference between Cp and Cv, significance of Debye temperature, and a few problems which will be worked out. In continuation with what I have been talking to you so far, I mentioned about the bond cyclic condition. This cyclic condition is the one which is not unique for the lattice waves that are passing through the solid. That is the one that we are discussing at present. It is important to note that this is validity both for electrons as well as magnons. What about electrons in solids? You have electrons residing in the valence band and conduction band, something like I showed a lower branch, upper branch here in the case of lattice waves. Similarly, in the solids you have got electrons in the valence band, conduction band, and semiconductors and so on. There again the bond cyclic condition, whatever that I have written here holds good, right, not only for one dimensional solid, but also in general for 3 dimensional solids. So, we now move on to what are called phonons, and you all know about photons. You have the light coming from a source, it is light coming from sun or a star or a moon or the moon or from any source that you have got here. This hall, light consists of photons. You see light travels in the form of waves, but according to quantum theory which was given by Max Planck, light radiation consists of what are called photons. Similarly, now the lattice wave that is propagated through the solid, we have been talking about lattice vibrations or the lattice waves, and all the lattice waves can be quantized. The quantum of the lattice wave is called the phonon. The analogies work according to Planck's formula. The average energy of a harmonic oscillator is given as the average energy of the oscillator will be epsilon will be h bar times omega by e to the power of h bar omega by k t minus 1. The number of quantized vibrations n is given as this energy divided by h bar omega, that gives the number of phonons. So, remember the number of phonons is nothing but the energy of the oscillator divided by h bar omega. These quanta are called phonons in analogy with photons, and the concept of phonons is useful in dealing with the interactions of electrons with phonons to explain electrical conductivity and superconductivity. In principle, what is electrical conductivity? You say that atoms are vibrating, the atomic vibrations are equivalent to phonons, and so the atomic vibrations hinder the flow of electrons, right. The atoms are not vibrating, the electrons will freely pass through. So, the electron ion interaction or electron instead of vibrating ion, I will say electron phonon interaction is responsible for electrical resistivity. Then we talk of Cooper pairs in superconductors. The phonons aid in the formation of Cooper pairs, the electrons are getting paired by means of phonon. That again I will talk to you in the next chapter. Now, therefore, the phonons play an important role in applying the electrical conductivity and superconductivity. We now talk about lattice vibrations in 3-dimensional solids. So far we have been talking about 1-dimensional lattice, right, monatomic or diatomic. We move on to a 3-dimensional solid. You will have planes of atoms, right, instead of only a line lattice, you will have planes of atoms because you have 3-dimensional solids. Now, there will be both longitudinal and transverse vibrations, and so you got a lattice here. Imagine you have a set of atoms in this plane, then you have again a set of atoms in this plane, a set of atoms. These dark continuous lines are, they refer to the planes, right. Then you have this plane is not displaced, but you see when you are pulling or the lattice as a whole is vibrating, you know, the S atom you have here S minus 1 and S plus 1 plane. Now, these planes are connected to each other as in the 1-dimensional case. This plane moves here, right, this plane moves much further. This is a longitudinal vibration. So, similarly you can have a transverse waves, right, you have the transverse waves as well as the longitudinal waves, and so for every frequency there will be 2 transverse and 1 longitudinal. Okay. There will be 2 transverse vibrations and 1 longitudinal vibration for the atoms in the different planes. So, in 3-dimensional crystals. Now, we wrote down the relation connecting omega and k. Such a relation can be formulated for 3-dimensional crystals also by taking into account, if you have got one atom here, then you had in the earlier case you have atom here, you are taking into account only the nearest neighbors. For a 3-dimensional solid, for truly calculating the phononic band structure, I mentioned about phonons. By phononic band structure, what I mean is a relation connecting omega and k. I will have a graphical representation which shows how omega behaves, or omega as a function of k, right, omega varies as a function of k in a little while, and that is the so called phononic band structure for a 3-dimensional solid. For a 3-dimensional solid, it is obvious that you have to take into account all the interactions. You have got an atom here, the interaction coming from this, and the atoms in the y direction, the atoms in the z direction, all the atoms, as many atoms as possible, their Coulombic interactions are to be taken into account, and you have to calculate the effective potential, right. That is the one that then you have to form a what is called a dynamical matrix. Now, these things are above your level. Eventually, you can have a relation connecting omega and k, and the relation that you get connecting omega and k can be verified by experimentally by performing inelastic neutron scattering experiments. Now, p square by 2m is the kinetic energy. The kinetic energy is the incident neutron, where mn is the mass of the neutron. Then the scattered neutron will have a momentum h bar square k prime square by 2 mn plus or minus h bar omega by 2 pi. So, the phonon dispersion relation omega k are most often determined by inelastic scattering of neutrons with the emission or absorption of phonon. So, this is the phonon energy, right. Something like a Raman effect or Compton effect, you have a neutron incident on a solid and or a medium, then the scattered neutron will go with a different momentum. You have got k square and k prime square, right, and then some energy is absorbed or emitted, or some energy lost or gained, and there will be emission of a phonon, okay, or absorption or emission, and this is the phonon energy. So, this phonon energy will be coming here, and that will give you a relation connecting. You got, note that you got omega here, radians per second, you have got omega here, you have got k here. This is the so called a very important dispersion relation. Maybe in our country very many atomic energy scientists that we had in Pokhran 1 and 2, they got their PhD in the area of neutron diffraction or lattice dynamics. They worked in this so called is a big area called lattice dynamics, and ultimately what you get is you talk of lattice vibrations, ultimately you end up with a relation connecting omega and k for all kinds of solids, uranium, thorium and so on, or very many systems of interest, and you have how atoms behave at different temperatures. You have omega and k relation, okay, and these were diamond, right. This is a theoretical curve, obviously this continuous line is a theoretical curve and the experimental points are found here. These were diamond. Ta refers to transverse acoustical, La refers to longitudinal acoustical. I mentioned about transverse and longitudinal. To is the optical mode, transverse optical, Lo is the longitudinal optical. Therefore, as we had in the monatomic case, you have the acoustical branch and then the optical branch. Now you have got both the transverse and longitudinal modes. The continuous line is the theoretical line that you have to formulate for as we did in the one dimensional case, monatomic and diatomic, we have to have the force constants ought to be taken into account for and you have to form a dynamical matrix connecting omega and k. The theoretical curves are obtained, and the important point to be noted is how beautifully the experimental points or the experiments and theory they support each other, in the sense that very good agreement between the experiment and theory, because they are the experimental points lying on the theoretical curve, right. You see the experimental points, they are very beautiful. The theoretical evaluation has been very good because the experimental points obtained from inelastic scattering of neutrons, the experimental points lie very close to the theoretical curves. The agreement is very good. This is the dispersion curve obtained for diamond. What dispersion curve means, how the frequency of vibration of the phonon changes as a function of k. For a different values of k, what are the possible frequencies, right. For a particular value of k, omega values are given here, right. Okay. This is what you end up, and the agreement is very good. Now, here comes let me have a digression. This problem of diamond was became a serious problem between two Nobel laureates, Sir C.V. Raman and another famous physicist, Max Born. They were at loggerheads, and of course, they had their opinions were different, and Sir C.V. Raman we understand was very adamant, and it became led to personal enmity between C.V. Raman and Max Born for the diamond problem, right. This is a very important view graph which shows the relation connecting omega and k, okay. That is the end of your study on lattice vibrations. This is for a 3-dimensional solid. Obviously, it is a problem which has to be dealt with at a PhD level. Of course, this is one slide I am showing. Now, let me pass on to some of the important comments. You know, I mentioned earlier in my earlier lecture also, very often the students at the BSc level or even at the higher levels, they do not understand the significance or the difference between CV and CP. I told you CP is the one which is experimentally measured. It is easier to measure CP. CV is the one that can be theoretically determined, because simple reason, thermodynamics says CV is equal to dE by dt. What is E? E is the energy of a solid. If there are n atoms, they are equal to 3n harmonic oscillators. What is the energy with each oscillator? That is how we evaluated, Einstein evaluated or Debye evaluated 3n times the energy of the oscillator. So, the energy of the solid can be obtained, then you have to find the derivative of that energy with respect to temperature to determine CV. So, for the theoreticians it will be easier to evaluate CV. For the experimentalists, they measure Cp. What is the difference between Cp and Cv? Cp and Cv are connected by a relation of this kind, and you have got what is called gamma, the so called Grunheisen constant gamma coming here. Alpha V is called the volume expansion coefficient, that is the thermal expansion coefficient, it is the bulk volume expansion coefficient, and gamma is the Grunheisen parameter. And the important point to be remembered, Cp almost is equal to Cv, because the difference between these two is very small. I was talking to the youngsters, you should be knowing the difference between Cp and Cv. You see the specific of water is 1. 1 means 1 calorie per gram. If you take 1 gram of water, the heat required to raise its temperature by 1 degree centigrade is 1 calorie. That is what you mean by specific heat, right, the thermal energy required to raise the temperature. Now, this whether it is Cp or Cv you do not know. For solids, for gases one can talk of Cp and Cv, the specific of a gas at constant volume and pressure, and you should be wondering why should you talk about Cp and Cv for solids, right. What is meant by the specific at constant volume and constant pressure, but these things really exist, they matter much, otherwise your Grunheisen parameter should become 0, right. The Grunheisen parameter is again an important parameter. If it becomes 0, Cp will be equal to Cv, right, but that is not a real thing, right. Cp and Cv are related by the so called Grunheisen parameter, but the important point is, as you are concerned, the difference between Cp and Cv, as it will show you, is very small. Okay, this is the Cp Cv, this is Cp that is experimentally measured, the Cv that is theoretically evaluated. It is easier for the theoreticians to evaluate Cv and instead of Cp. The variation is very small, only 2 to 3% the variation is small, and so it can be ignored. The Grunheisen constant, this variation that you got here only varies from 2 to 3%, it can be ignored. And we will now work out some problems from the theory we have seen so far. Calculate the heat capacity of copper with the given data. The atomic volume V naught is equal to Cv is here, okay. The other things are atomic volumes known, the compressor rate is given, coefficient of the thermal expansion is given, the Grunheisen parameter is given 1.9, okay. I mentioned about Grunheisen parameter just now. So, you write the Grunheisen parameter as the thermal expansion alpha, you have got here V naught volume, K is the modulus, the compressibility, right. Cv is the heat capacity, then your Cv becomes this much, right. Cv is equal to gamma will come down to the, so substitute all these things, get your Cv to be equal to this much, right. So, for the problem that I mentioned, calculate the heat capacity, that is the value of Cv, heat capacity is nothing but Cv, right. Cv equal 3.8 into 10 to the power of 2 joule per kilogram, right. I mentioned about calorie per gram, the conversion between calorie and joule. So, Cv works out to be so many joules per kilogram. The second problem will be a very interesting problem. Use the Lindemann rule. I have not mentioned so far the Lindemann rule. Now, it is time for me to mention not only Lindemann rule, some of the other relations as well, because of the importance of the Debye temperature. I am repeatedly telling about the significance of the Debye temperature, and so the problem goes as follows. Use the Lindemann rule to calculate the Debye temperature for copper, whose melting temperature is 1356 Kelvin, the atomic volume is so much, atomic weight is this much, and then you are asked to compare the Debye temperature values obtained by other methods and give your comments. The statement I have made, compare the Debye temperature values obtained by other methods. So, it is possible to extract Debye temperature from other methods, or there should be relations connecting Debye temperature and electrical resistivity, Debye temperature and superconducting tungsten temperature, Debye temperature and elastic constants, Debye temperature, so the other the Debye-Waller factor. Now, therefore, Debye temperature is found in very many places. That is the reason why we give considerable importance to Debye temperature. according to Lindemann rule formulated by Lindemann in 1905, but even today Lindemann rule is used to determine the melting temperature. Once the debye temperature is known, the melting temperature can be determined. The nanomaterials have gained so much importance. Now people try to go back to the melting temperature, why the melting temperature is coming down for nanoparticles as a function of size. It is a very interesting problem, it is a different problem, but the Lindemann rule again is being used in for other reasons. So, the constant K is 138.5 that is given. You are asked to calculate the melting temperature Tm, B is the volume of the material, other things are known. Substitute all these known values in this relation that you have got here and evaluate Tm, right. You are asked to use the Lindemann rule to calculate debye temperature. So, try to calculate the theta m. Theta m, what is m? M is the debye temperature coming from melting. It is called the Lindemann rule of melting criterion. So, theta m looks like 335 Kelvin. The important point is theta s. S refers to the melting temperature obtained from the true debye formula. S refers to the specific heat. Actually, debye temperature came into existence in the study of specific heats. Now, R stands for resistivity. I told you the debye temperature is connected to electrical resistance, right. E refers to elastic constants, right. So, the debye temperature is related to very many other phenomena. Therefore, the debye temperature according to specific heat is 342, according to Lindemann rule the melting is 335. From resistivity data you get 336 Kelvin, the elastic constant is 345 Kelvin. So, the superscripts as I told you M, S or refer to E, they refer to melting, the specific heat and then the resistance and elastic constants. Okay. Comments are the differences are not very much, but important point is this is the true debye temperature. But anyway, however, you try to express resistance in terms of you have the very many laws which connect the properties like resistance, elastic constants, melting, all these things connected to debye temperature, right. But this is a true debye temperature, that is because the debye temperature itself came into existence in the study of specific heats, right. So, the comments are the different physical measurements such as melting point, heat capacity, resistivity, elastic behavior, they are all related to debye temperature and different approximations are used, and therefore, there will be slight deviation for the resistivities for the debye temperatures evaluated by different relations, right. Even the superconducting transient temperature depends upon the debye temperature. Okay. Now, that is to illustrate the importance of debye temperature. What is the problem 3? In the problem 3 again you have the elastic constants C11, C12, they are the elastic constants. The elastic constants are related to debye temperature. Okay. That is to show that very many properties can be expressed in terms of debye temperature. Calculate the debye temperature of aluminum whose elastic constants are in 10 to the power of 12 dynes per centimeter square. C11 is given, C12 is given, C44, they are elastic constants, right. Elastic constants values are given. Its lattice constant E, the cubic lattice, right, aluminum is cubic, FCC lattice, the density is given as 2.7 grams per centimeter cube. For cubic systems, the debye temperature is expressed in terms of elastic constants as follows. For HCP structure, there will be additional lattice constants, right. Only for cubic system, you will have 3 constants C11, C12, C44, right. These values are given here, C44. You substitute these values here, then S is the number of atoms per unit cell, the Planck's constant, Boltzmann constant, S, and all these things come here. Okay. S is the number of atoms per unit cell, the atomic volume, density. So, density, the unit cell volume, S is 4 here, A is here and so on. Volume of the unit cell is obviously 4.05 angstrom 10 minus 8 to the power of 3. By substituting for the constants, we get the value of debye temperature as 400 Kelvin, whereas the experimental value is 390 Kelvin, right. From these problems, one should understand the importance of debye temperature. The debye temperature being related to elastic constants. In the earlier problem, the Debye temperature related to the Lindemann rule of melting. The melting point is related to the Debye temperature, right. Okay, you have got Debye temperature here, melting point here. With this, we try to close the section on this thing, and I would like to again tell you, when you look at the Grunheisen formula again, which I showed the relation connecting Cp and Cv, and Cp and Cv here, alpha V is the volume coefficient, gamma is called the Grunheisen parameter. I mentioned that Cp and Cv, they differ only by a very small magnitude, which is of the order of only 2 to 3%. The difference between Cp and Cv is nearly very small, it is negligibly small, it is only 2 to 3%. Gamma is called the Grunheisen constant, it is depending upon temperature and pressure. Alpha V is called the volume coefficient of expansion, you know the linear coefficient and volume coefficient. Let me now try to give the significance of Debye temperature to a more extent. The important point is caution is to be exercised while using Cp and Cv, right. Now, you should not be getting confused between Cp and Cv. I told you Cp is experimentally measured, Cv is theoretically it is easier to deduce Cv. Debye temperature is used to calculate the following things, right. Superconducting transition temperature has been often calculated even today, the superconducting transition temperature for the conventional systems which obey the Bodine-Cooper-Scheriffer theory, about which I will be talking to you in the next chapter. Now, the Tc, the superconducting transition temperature Tc is related to the Debye temperature. Again, the electrical resistivity given by Simon, you have got a Simon's formula, where the resistivity rho is again given in terms of the Debye temperature. I told you about the Lindemann rule or Lindemann law of melting criterion. The melting point Tm is related to Debye temperature. Debye-Waller factor, Waller is a well known physicist, the Debye-Waller factor is expressed in terms of it contains Debye temperature. The problem which you showed, the elastic constants are again related to Debye temperature. Let me now go to the summary part of my last lecture on this particular topic. The omega versus k obtained for a diamond from theory and experiment, the agreement is very good. Inelastic neutron scattering experiments give, they are the direct experiments, right, which they give the omega versus k curves. Cp gives the experimentally measured heat capacity, whereas the theoreticians obtain Cv because of the reasons I told you earlier. The difference between Cp and Cv is only 2 to 3%. Debye temperature plays a significant role, as many solid state properties which I mentioned earlier are related to this parameter. Let me now pass on to the question session. The first question is, why is it easier to determine Cv? How are Cp and Cv related? What are the various properties which depend upon Debye temperature? With this, we come to the end of our lecture series on the chapter on crystal structure and thermal property of materials. Thank you.